Yeah, so good evening, everyone. Yeah, welcome back to Plan 258. Yeah. So in today's agenda, we will discuss about decision under utility and group decision. Okay. Everyone can see my screen.
Just the meeting agenda, sir.
Huh?
Just the meeting agenda.
Oh, yeah, the meeting agenda. That's correct. Okay. So please be reminded that you have a progress report on April 25, okay, because next week we will have no class. So because of the Easter, yeah. So happy Easter for those who celebrate this. Okay, so let's start with the first part, which is utility theory. You see the slide?
Yes, sir.
Good. Okay, so this is the part that we discussed last week. Okay, so this is just continuation of that. Okay, so in this slide, we will discuss the following topic. Yeah. First, we will discuss about certainty versus Campbell, and then we have two Campbell problem, and then our attitude toward risk. Okay, and then we will discuss about what is utility and utility function, and how to compute the expected utility and risk premium, yeah, or certainty equivalence. Okay, so this is part of decision analysis. Okay, so we have discussed a few weeks ago about decision under certainty and under uncertainty, and then last week we discussed about decision under risk, right? So with decision tree and so on. So you have the assignment of that, and then today discuss about this topic, yeah, decision under utility. Okay? And today we will also discuss about group decision making. Yeah? So after the holiday, okay, we'll discuss about game theory, yeah, with this decision under conflict. Okay, so now suppose you have two choices. Yeah? Let's name it option A and option B. Okay. So option A is guaranteed to get 60,000 US dollar. And then option B, you have 50% chance to get 150,000. But you also have, oh, this is negative now, loss, negative 30. Okay, so which option do you prefer? Okay, so if you compute the expected value, okay, so 50% times 150 plus 50% times minus 30, this is minus, okay, you will get exactly the same 60. So try to grasp this problem first, and then tell me which one do you prefer, A or B? Okay, let's see. Yeah, both are 60. If you use or yes, if you use risk analysis, you cannot decide. That's correct. So, but you can still decide, right? Based on your preference. So it's not based on logic, just based on your preference. Which one do you like? Okay, someone
option A.
Yeah, you choose option A. Or some people choose option B. Okay. Good. So, tell me why you choose A and why you choose B.
Sir, at first, I guaranteed 60,000. In the option B, at first, you have a 50 chance to lose 30,000. If you don't have money, you have utang already 30,000.
Okay. So you prefer A because it's guaranteed 60 without a possibility of losing, right? So this is what we call certainty versus gamble, right? So those who choose A prefer certainty. Those who choose B prefer gamble because higher risk mean higher gain, but there is also possibility of losing. Okay, so those who choose B, why? Yeah, higher risk, higher reward. Okay, good. There is actually a perception difference. Okay, so number one, let's call this X. Okay, so you get the difference between 60,000 success and then negative, with this 30,000 failure. Okay, and then the other one is 60,000 success and then 150,000 success. So if you feel that X is greater than Y, then you select A. Okay, so now in this lesson about utility theory, we want to quantify this feeling inside our heart that we prefer A or B. Okay, so there is no right and wrong, okay, where you choose A or B, but we will use this to reflect about who we are. Okay, so let's play another one. Okay, this time you have two gambles. There is no certainty. Okay, so let's call this two gambles problem. Suppose you have two gambles. Let's name it gamble A and gamble B. Okay, so gamble A, you have 1% chance. Okay, this is like a lottery. It's a small percentage. You will earn 100,000. Okay, but 99% you get zero. In gamble B, okay, you have 50% chance to get 2,000. And then 50% chance you get nothing also. Okay, you have nothing to lose, right? So which one? Okay, Lay said she likes gamble B because I have higher probability of winning. Okay, oh, many of you prefer gamble B. Who choose gamble A? Okay. Oh, Archie choose gamble A. Okay. So tell me why you choose gamble A and why you choose gamble B. Higher payoff for gamble A, yes, of course, but also lower probability for that. Okay. Why you choose gamble B? Majority of you choose gamble B. Okay, B is too slim chance to win. So yeah, the expected value for those two gambles are the same, exactly the same. Okay, so in practice one, if you want to compute, okay, so can you draw the decision tree of two gambles problem and then can you compute the expected value? Okay, if you just use maximum EV like in the risk analysis last meeting. Okay, so you will probably draw it this way. So gamble A, gamble B, win and lose. And then you get exactly this. And then when you compute, okay, you will get EV 1000 and 1000. So you cannot decide based on maximum EV. Yes, gamble A is like lotto. That's correct. Okay, so just based on risk analysis, this doesn't work. But if you need to choose between these two, okay, sometimes life will make you face this kind of problem. Okay, so if you need to choose between the two, which one is the two least evil? Okay, so if you still need to decide which one you prefer, gamble A or B. So I will choose A if it is bigger, appealing win. Okay, so whatever you choose, A or B, it doesn't really matter. Okay, both are right. Okay, because those are your preference. Okay, so but your choice, yeah, the same EV. Okay, so your choice is actually reveal who you are. Yeah, this is what decision analysis is about. Yeah, it's a kind of mirror about who you are. Okay. So if you choose, gamble A, so the EV is 1000. The price is higher than gamble B. Probability of winning is small. So if you choose A, you are risk lover. Okay. So if you choose gamble 2 or gamble B, the same EV, the probability of winning is actually bigger. So this is safer. So if you choose gamble B, you are risk averse. Okay. So it's just showing your attitude toward risk. This is not right or wrong. Majority of people are actually risk averse, including myself. Okay, so here, these are the three types of decision maker, based on decision analysis under utility. So we can divide three types of decision maker. One is risk averse, second is risk neutral, and then risk taker. So risk averse will prefer shorting to gamble. So if you have choice between shorting and gamble, okay, you will choose A in this case. But now if you have two alternatives, both are gambles, okay, with equal EV, okay, you prefer safer gamble. So if you are risk averse, okay, here you choose A, and here you choose B. Okay, so of course, when one gamble have higher EV than the other, you select with lower EV if it appear risky. Yeah, so you are avoiding the risk basically. Yeah, risk neutral is indifferent. Okay, about between the shorting and gamble, so they cannot decide because this is basically based on risk only. Okay, so if the alternative are gambles with equal EV like this, okay, again they are indifferent. But if one gamble have higher EV than the others, okay, so then it will select based on higher EV. So risk neutral is using the risk analysis only, not using utility. Okay, and the third one is risk taker. So risk taker prefer gamble to shorting, and this is where the decision analyst is trying to explain why people still buy lotto, okay, even though the EV is actually bad. Okay, so if you choose between these two, yeah, shorting and gamble, okay, risk taker will prefer B, with this gamble. Now, if they have alternative, the two alternative are gambles with equal EV like this, okay, it will choose riskier gamble, yeah, A. Now, but if one gamble have higher EV than the other, okay, it will gamble with the higher EV. Okay, so apparently still logical, yeah. If you start to think this way, they are okay, actually logical, yeah. What it seems irrational is now become rational. Okay, so for that we need to quantify. Okay, so this quantification is called utility theory. Okay, so utility theory is an approach to assess risk attitude quantitatively. So we set an ordinal number. Okay, so ordinal number, as you recall, is just any number, okay, that have order and distinction, but you cannot take difference or multiplication. Okay, so there is no scaling here. Okay, so utility is just a quantified decision maker relative preference. So order matter, okay, for particular situation or particular outcomes. So here it is how you create utility. Okay, so utility is a measure of total worth of a particular outcome. So this is an example. Okay, how are you going to make utility? So you set any value, the highest value and the lowest value, usually negative, the lowest, and then you can set any numbers there in between. Make it in order, okay, from the minimum to maximum, okay, and then you set utility value. Okay, the minimum will get 0, the highest will get 1 or 100, whatever number, yeah. So, and then of course you will put something in between in the order. Okay, it will not go down from the minimum to the maximum. Okay, the maximum is now 1, the minimum is now 0. Do you understand this or not? So you have a payoff, okay, any value that you want to put. Say this is the example, okay, negative 500 up to 2000, for example. Okay. And then from the minimum you put 0, the maximum you put 1, okay, and then in between you just fill up the value that you feel. If I, for example, yeah, if you lose $500, okay, your feeling is 0. Okay, if you win, okay, $2,000, your feeling is 100%, your happiness. Okay, so now what happens if you lose 100? Okay, of course not 0, so it's say 5%, like that. Okay, if you get 0, okay, not winning, not losing, okay, then of course this is must be a little bit bigger than losing, right? So same, make it 10% and so on. So you can fill up all of these numbers. Okay, so now using this kind of table between payoff and utility, okay, then you can plot. Okay, so if you plot the utility, okay, and then you can fit into function, right? So utility function is a measure word by transforming the values into utils or utility values. Okay, so the X here is the payoff. Okay, and then now if I know the X, what is the value of utility? Yeah, again, utility is just 0 to 1. So this is similar to normalization. Okay, but this is normalization of your own preference, your own happiness. Okay, so here is the most used utility function. Okay, so let's discuss this function. Okay, number one is polynomial function. The second one is exponential function. Okay, so if you are using polynomial function, okay, and your risk attitude, yeah, is risk averse, so you can use square root of x. Yeah. Remember, x is your payoff. Okay, but if you are risk taker, so you can use x squared. Now, if you want to use exponential function, okay, and if you are risk averse, then you can use this function. So 1 minus exponent of minus x divided by r. Okay, so this r is a parameter, okay, that you can set. So exponential function is more general than polynomial. Why? Because you have parameter here. Okay, but if you are risk taker, you use this function. Yeah, e of x per r minus 1. Yeah, the same r. Okay, so let's plot this. Yeah, let's discuss about the first function with this polynomial. Yeah, remember square root and x squared here. So, what is the advantage and disadvantage of using this polynomial function? Yeah, square root, this one, can you see? Risk averse is the one on top. Okay, and then risk taker is the one that bottom like this. Yeah. So the nice thing about polynomial utility function is you can normalize, okay, the x value to 0 and 1. Okay, and then you don't need to care about any parameter, right? So it's just x squared or square root of x. Okay, but because of that, we also have a problem if you have negative payoff. So in that case, your negative payoff must be scaled up, yeah, by adding maximum cost, and then you take the absolute value so that the minimum will be 0. So you need to sift the graph. This is one way to solve the problem of negative payoff. Okay, so how about the second one, which is exponential function? Yeah, so let's discuss about the exponential function now. Here, okay, I compare exponential function and polynomial function. Yeah, the green is polynomial, and then this one polynomial also, and then the blue and the red are exponential function, yeah, with different risk parameter. So now from here we can start to see, okay, that a risk taker is always down here. Okay, so risk taker is convex, convex curve. So this means the second derivative is positive. Second derivative is positive. Okay, risk averse is on top like this. Okay, is concave curve. Okay, so that means there are certain point that the second derivative become negative. While if you say how about risk neutral, that one will become a linear line, yeah, straight line there. Okay, so now I want you to do this. Yeah? Just put a few minutes Okay, I want you to evaluate yourself, yeah, each of you. Okay, put your own value. Okay, you can set up any payoff value. Okay, creates this kind of table and this kind of plot. So it's your personal. Okay, again, there is no right or wrong. Okay, so that you can start to see your own attitude toward risk. Okay, are you risk taker or risk averse? Okay, once you do that, okay, can you share your plot? Is it clear or not? The instruction.
Here's sir.
Yeah, good. So you create something like this. So you can put your own payoff. What is the most negative loss, okay, that you think you can bear, and what is the maximum payoff that you can feel happiness? Okay, so you put it 1 and 0, and then you feel something in between. Okay. So I will set you as co-host so that you can share. Okay, so everybody is co-host now. I'll stop sharing and now is your time. First, can you share to the others?
Hello. So I just shared a screenshot. So I set the 0 to half utility. So
Okay.
because I think my neutral stance is I don't get anything. But
Okay.
since the least is negative 500, I set that to 0 and 2000 is to 1. So and because the increments of 100, 250, and 500 is minimal. Compared to 1,000 and 2,000. So I made the step 0.5, and then
Okay.
since 500 to 1,000, 1,000 to 2,000, it's perceptionally bigger. I mean, you can say that it's just times 2, but if you compare like 100 to 2000, that's 20 times bigger. So I made the jump so bigger. So like from 0.65 to 0.8, then from 0.8 to 1. So it's a bigger step up. So
Okay.
that's just my perception.
Yeah. So based on this plot, okay, roughly, I can say that you are risk neutral when negative, and then risk neutral to risk averse, a little bit risk averse, but mostly risk neutral.
Neutral.
You are
Okay.
very logical.
Mhm.
Based on this, if this is your true preference, then that's the conclusion.
Okay. Thank you, sir.
Yeah, thank you. Yes. Anyone else want to share? So give me the plot, then we can interpret that plot. I think that's interesting. Anyone else? Okay, so I'll share what is in the slide then. All right, so if we choose these numbers that I just put there, okay, so many people will have this kind of plot, yeah. So if you look at this, when it is negative, okay, suddenly this person become risk taker. Can you see how this is how it become risk taker? Can you see the curve? Okay, the curve here is the same as this one. Okay, so this is the curve of risk taker. Can you see that? So risk taker curve is convex. Okay, so can you see the pattern of the curve? Okay. And then when positive payoff, okay, suddenly this person become risk averse. How can I say that? Okay, risk averse, you can see the pattern. Okay, the pattern of risk averse is concave. Okay, this. Is it clear or not? So based on your own plot, so you can conclude, yeah, you can interpret that plot. Yeah. So say this is example that this is risk taker when it is cost and risk averse when it is gain. So price a while ago is practically almost linear. So in that case, risk neutral. Okay. So anyone else want to share your own preference on these numbers? Go ahead. Yeah. Lei, you want to share to others? Is it okay?
Yes, sir. I will send to everyone also. I tried using the square root of the for the utility so that I'll get risk averse. So for the payoff, it's the highest that I can, if say if I change job and I want a bigger salary. So the highest that I'm expecting is additional 30,000 if I'm ever gonna shift. So that's my utility is 170T. And then if it's 20,000, it's 141 approximately. And then if 10,000, it's 100. And then 0 if there's no change in pay grade. And if it's negative 5,000, it's minus 70, and minus 100 if negative 10,000.
Excellent. So if it is negative, okay, so you are more risk taker, and if it is positive, you are more risk averse. Yeah, in this plot, yeah, this and this plot, right? Not extreme risk averse, still a little neutral. That's okay. The concavity, yeah, the concavity represent how extreme you are in risk averse or not. Yeah, it's closer to the straight line, so you are more on the risk neutral. Okay. So anyone else? One more? Come on. Anyone want to share your own preference? Did you get
Sir,
the
just to validate,
yes?
the utility is always on the y-axis, right?
Yes, the vertical axis.
Okay.
Okay.
Thank
So
you.
the vertical axis is utility, and then your horizontal axis is the payoff. Do you want to share your screen, Ms. Cervantes? Yeah.
Bye.
Or you can share the screenshot to others also. Is this clear, the meaning of utility and how you interpret? Okay. Maybe some of you shy to be interpreted whether you are risk averse or risk taker. It doesn't matter. Okay, it's just okay. Anyway, so let's continue then. Yeah. Now, majority of people are actually risk taker. Yeah, to risk neutral. Okay, so most decision maker are risk averse to neutral. Okay, that's why I highlighted the utility function. Okay, this is the utility function for risk averse. Can you see the table earlier? Yeah. So there. Okay. Remember, we have two type of function, polynomial or exponential. Okay, whether this is risk averse or risk taker. Okay. So the one that I highlighted here with yellow, okay, this is the one that we will use. So if I don't tell you in exam or in the quiz, okay, so if I don't tell you what utility function, so you can use this yellow exponential or risk averse. Is that okay? So let's come back here. So now let's discuss what is the meaning of R here. Yeah. So this is called risk tolerance parameter, yeah, or shape parameter. So you can start to see the meaning, yeah, by plotting for different R. Can you see? If R is small, okay, this one, the blue one, if R is small, so actually is more risk averse. Okay. When the R is very big, it is more risk neutral. Can you see that? Okay. So the value of R represent the risk tolerance. Okay. So smaller R, more risk averse. Okay. Going to the toward this direction. So going toward there is more risk averse to the left, top left direction. Okay. So now what will happen? Okay. Can we find the value of R? Okay. So can we find the value of R based on actual number? See, in that case, you need to know, okay, the win payoff, okay, the lose payoff, and its probability. Okay, then you can get the value of R. So suppose you know the win payoff, okay, with certain probability and lose payoff with certain probability. Of course, the total probability must be 1, right? So then you also know the indifference. Yeah? So 1, 2, 3, 4, 4 numbers, the input. Indifference between playing lottery and getting C with certainty. So this is the game certainty versus gamble earlier. Okay, so say I put here 0.5 and 0.5, okay, for the utility of L, meaning losing. This is utility of H, meaning win. And then this is indifference. Okay, so now we said earlier the utility function to be this way, right? So then we can include, okay, because 1 minus something, so we will get all the same numbers. So we can put into this kind of function, isn't it? Okay. Then from here, because you know H R, oh no, H, L, and C. Yeah. So because of this probability that you said, then you can calculate the risk tolerance, okay, using Colsic. So this is an example. Okay, so you said, say for example, H is 1, L is 0, and C is 0.5. Okay, and then the left-hand side is this equation. Okay, and the right-hand side is this equation. Okay, and then you take the difference, okay, this to be your target between the left-hand side and right-hand side. So set this target cell to 0, okay, by changing the R. Then you will get the value of R. So can you try this in your Excel? Did you get the same number or yeah, about this number? Is that right? So I set in Excel. So these are the numbers that we put. The left-hand side. Okay. So you multiply the probability and then 1 minus H, okay, divided by R, right? Same thing there. Okay. And then the one in yellow here. So the right-hand side is just 1 minus this one. Because probability is 1. Okay. So this is Campbell versus certainty. And then you go to what if analysis and goal seek. Okay, so set the difference to 0, okay, by changing the R. Okay. Yeah. This big R represent almost risk neutral. Yes. Yeah. The value can change depending on the initial value. Yeah. Yeah. Okay. Very good. Vin. Yeah. Is it clear how to get the value of R? Anyone want to share? So if you have the exponential function, so we can get the value of risk tolerance, okay, by inputting the actual value. Okay. So what happened if to your risk tolerance of exponential utility? Okay. So if your win payoff is actually a different number, so once you make that, you can actually do the next practice. Yeah. This one. So what will happen? Can you find the risk tolerance of the exponential utility function? Now the H is 1000 with probability of 0.25, and then L is minus 500. This is probability. And then the C is now 250 for indifference. Okay. So you need to make the value between the absolute value of X is between 0 to 1. So that means negative 1 to negative 1 to positive 1. Okay. Otherwise, your exponential value will blow up very big. Okay. Well, I have no answer for this, so can you start to make this? Anyone want to compute that? Practice? So if this is -1 and this is 1, so what is C? Okay, so you need to rescale this X, which is the payoff value, should be within 0 and -1 to +1. Okay. So this need to be rescaled. After that, you can compute the same as before. Yeah. This. Okay. Anyone want to share screen for this? Computing risk tolerance. Bit difficult. So if you have your value is 1000, this is the maximum, right? And your minimum is -500. So, and then this is now become 1, and this one becomes 0. So my question is, C in here is actually 250. So what is the value of 250 in this scale? I draw this in the chart. Okay, so I think the drawing is reversed. That's fine. Right. So this is the X. Oh no, this is the actual payoff. And then this is the X. Right? So then you can plot this one. So if you have 1,000, you get 1. And if you have oh, that's why it's wrong. So this is negative 500. There. So if you have 1,000, you get 1. And then if you have negative 500, this one, you're supposed to get 0. The plot is not correct. Create a plot. And isolate the data. First one is supposed to be the X. So this one. And then is the value. The second one I just removed. There, this is the correct plot. Right. So negative 500, okay, and then 1,000. So in this case, if you have 250, around, what is the value? Zero 0.5, is it 0.5? So if you put it as 0.5, it will not work. So I will put different numbers here. Okay. So I add another data point. So with this X is this value, and then the Y is that value. Yeah. So trying to make this okay, computation, and then we'll put this into your assignment if you cannot finish this. This practice. Someone make it. Oh, okay. So, Vin, you want to share your screen?
Okay.
Hmm. If you use only 1,000,
Yes, sir. Okay, if the highest value is 1,000 with the probability of getting this payoff at 25% and then negative 500 for lowest payoff at 75%. So the left hand side is 0.25 times H, the H over R minus H over R of EXP, then plus 0.75. But what I did here is I just multiply the right hand side by 4 so that we get 1 for H over R and then 3 for the L over R.
okay.
And then using goal seek, we set this target cell to a value of 0 by changing R.
Yeah. The problem here is the problem here is because you put the value is 1,000, and then if you put it into exponent, okay, the value is actually very big. Okay, so that's why we need to set these values, okay, into 0 and 1. This one.
So we normalize this H, L, and C.
Correct.
Okay. So if we use the
1,000 become 1, right? Cannot be because now the 5 minus 500 now becomes 0.
okay. And then this one would become 0.5.
No. If you plot, okay, say a while ago like this, right? So your 0, this is minus 500, right?
Mhm.
500. And then 1,000 is here. This is 1. Okay. So so this one is actually 1,000, right? So then you need to find what is 250 here. Okay, so what is the value of 250 here?
It's 0.5.
Is it 0.5?
Yeah, by linear interpolation.
Okay, so if this is 0.5, then it's fine.
Yeah, actually 250 is halfway through between 1,000 and negative
Oh,
5.
yeah, that's correct. So this is 750 and this is 750. That's
Okay.
0.5, that's correct. Okay, so
Then I'll use goal seek again.
yes.
Mhm.
See the same number.
Oh, alright.
There.
Okay. Then R is
Yeah, smaller. Yeah. Okay, thank you, Win.
Thank you, sir. So we need to normalize to lower values.
Otherwise, exponential function tend to blow up very big or very small.
Mhm.
Yeah.
That's why on my first try, it's like a dumping function. Okay.
Okay.
Thank you, sir.
Yes, thank you. Okay, great. Let's go to the next attempt. So I said this is attempt. Can you see my slide? Okay. I need to share this one. Go. Okay. So this is an attempt. Okay. How are we going to compute utility of the expected value? Okay. So we have two Campbell's problem a while ago, this one. Okay. And let's use polynomial utility function, okay, for risk taker, risk neutral, and risk averse. Yeah. So this is the two Campbell's problem a while ago. Can we calculate the utility of the expected value? So when we said utility of the expected value, okay, UAV, okay, so this is we use exponent, a polynomial function, okay, for risk averse, risk neutral, and risk taker. So for risk averse, remember polynomial we use square root. Okay? And then for risk neutral, of course, this is already EV, so we use just the EV. Okay? And then for a risk taker, we use square. Okay? Now, this is an attempt. If you want to use utility of expected value, can we decide? No, we cannot decide. Yeah, because the utility of expected value, or UAV, is actually the same decision as EV itself. So this is not going to work. So don't do this. Okay. So then how are we going to make decision based on utility? So in that case, you don't compute utility of the expected value. What you compute is actually expected utility. Okay, can you see the difference? So expected utility, okay, so you calculate the utility first, okay, and then you multiply by the probability. So this is called expected utility, EU. Okay, so then the decision is because this is based on gain, so you can use argmax of this EU. Okay, so let's say you have the same problem as earlier. So we have two Campbell's problem like this. So how are we going to compute the decision, yeah, based on maximum expected utility value, so EU expected utility? Yeah. Again, we use assume polynomial function, okay, for risk taker, risk neutral, and risk averse. Yeah. Then you can start to see. Yeah. So when you are risk taker, okay, so you put the probability here. So 1% multiplied by the actual payoff, 100,000 square, okay, plus 99% times 0. So this is a very big number. Remember, when you are using risk taker, so what you will do, you square it. Yeah? So the same thing with Campbell P. So if you are risk taker, in this case, you compare the two. Okay, this is bigger. So in this case, if you are risk taker, you will choose Campbell A. Okay, if you are risk neutral, okay, this is basically EV. So in this case, you cannot decide. Yeah, this is exactly the same as expected value, right? So now if you are risk averse, okay, our function is now become square root. Okay, the same probability, okay, but we compute the square root of this payoff. Okay, then you can start to see, okay, if you are risk averse, you will choose gamble B. Yeah, if you are a risk taker, you will choose gamble A. Yeah, this is exactly what we expect. Okay? Based on different type of risk attitude, then you will select the decision. Is there any question up to here? Okay, so the point is, you need to use expected utility. Okay, don't use utility of the expected value. Okay, so you still need to compute with the probability to get that. Okay, so now I want you to do this practice. Okay, now you use exponential utility function for risk averse. Okay, I give you the risk tolerance value R is equal to 5. Okay, and I want you to practice to between two choices. Yeah, option A is guarantee payoff of 60, and then option B is 50 chance you get 150 and 50 chance you lost. Yeah, this is negative. This is negative 30. Yeah. So can you calculate which decision you will choose? Risk averse, yeah, you need to choose risk averse. Can you practice this? How do we get the difference? What difference you are asking?
Sir, it's okay now. That's
Ah,
my question way back.
okay.
Thank you.
Hmm. Um, Vin, you want to share your screen? I will stop sharing.
Okay. It's just getting the expected value of the utility function. So it's the probability times the utility per payoff. So for option A, the slide shows 0.9999. That's
Yeah,
very
yeah,
close to
yes.
1. Okay.
Wow.
And then
Wow.
for option B, that's negative 200.71.
Okay. Right, right. Yeah, this is 50 prime, 50, right? Negative. Yeah, correct. So the decision is to choose A.
Option A, because it's a risk-averse.
Right, because
situation.
the actual formula is actually for risk-averse.
Mhm.
Okay, so if you want, you can try also the formula for risk taker with
Okay.
yeah.
So we take this.
You can select you can put in different cells so that you can compare.
Okay. Copy and then
Yes, yes. So exactly the same, but now instead of 1 minus, now the exponent minus 1. That one is also reverse. So the exponent minus 1, yeah. 1 minus is zero. Okay.
too large. Let me use scientific notation.
It's yeah. This is the problem with exponent, so become very large. So in that case, you can remove the 1,000.
Mm.
Okay, so instead of 60,000, you can put 60 example.
Right here.
Yeah. And then the other one also, this one is now can 150, and then the other one is minus 30. Okay, still big, but comparable.
And now they're equal.
Now they are equal. Because the R value. Because the R value is supposed to be 5, isn't it?
Okay, let me-
Not 5,000. Okay.
Yeah, you'll choose option B now. If
Oh. Okay, we
That's
will
why-
choose option B now because the value is the function is actually for risk taker.
Mm.
Right. Okay. So thank you. Win.
Thank you, sir.
Yes. So we have seen, okay, how are we going to use utility, okay, with the probability to make decision, right? So then we can go to the next topic. Actually, is for insurance. This is based on what Rafi was asking last meeting. How about for risk premium? Okay. So risk premium, okay. Risk premium is an amount, is the amount, okay, that the individual is willing to give up, okay, to avoid the possible risky option. So instead of using utility, okay, now you put this into money. Yeah, so similar to EV. Okay. So now you put this into money. So we have what is called certain equivalent or CE. And this is the EV from the risk analysis last meeting. Okay. So then you can use this formula to compute, okay, either the CE or the EV. Yeah? So certain equivalent or CE is the number that represent the value, yeah, which if offered for certain will appear to the decision maker as being the desirable exchange, okay, as uncertainty or risky option. Okay. So this concept has been used for many years in insurance. Okay. So this is the expected value, and this is the risk on the horizontal axis, and this is the value in the vertical axis. So the expected value is this linear. Okay, of course, higher risk, higher expected value. Okay, and then the certain equivalent is this curve. Okay, and then the difference between the expected value and the certain equivalent is called risk premium. Okay, so you can also make decision based on certain equivalent. Yeah. So this is the example. Suppose, okay, there is a winning situation like this. Yeah, if you join a risky game, okay, you have 20% chance to earn 1,000. Okay, so you have 20% chance, okay, to earn 1,000. Okay, and then you have 80% chance to lose. Yeah, so 80% negative 125. Or, okay, you're not joining that risky games. Okay, so this is the, so alternatively, 100%, you will earn 75. Okay. Is the certainty versus gamble. Okay. Can you calculate the EV of this risky game? And then can you calculate the certain equivalent and the risk premium? So in this case, okay, your EV is how much? 20% times 1,000 and then minus, this is the negative. Okay, for gamble, EV is 20 multiplied by 1,000 minus 80% times 125. So the EV is 100. Okay. The CE is the lowest amount of cash that you will take to join that situation. So in this case, you have positive, right? 75. So the CE is that 75. Okay. Then the risk premium is just this one. Yeah. Risk premium is just CE. You put it that the other way. So become EV minus CE. Yeah. So EV minus CE. So in this case, you get 25. So up to here, is there any question or not? So the CE is something that you get with certainty. Okay. And then the EV here is only for the gamble. Okay. Now, the risk premium is the difference between the two. So what is risk premium here? Risk premium here is the money, okay, that you will give up in order to avoid the possibility of loss in the gamble. So that's why in the insurance, the jargon is exactly the same, right? This is your premium, okay? Meaning this is your risk premium. This is the money that you need to pay to the insurance in order to avoid loss. So if you have a project, okay, so you can compute this way also, right? So you have transport project, you have. So what is the certainty that you will get with 100%? Okay, and then what is the probability that you will get and you will lose? So from there you can get the EV. Okay? From there you can also calculate the risk premium. Yeah? Then how much insurance that you're supposed to get from here. Is this clear or not? Any question? Oh, clear. Okay, good. So in that, if this is clear, so can you practice next so that this become clearer? So let's use the previous problem. Okay, so we use this previous problem of this one. Can you compute 60 guarantee, and then this one is minus. So 150,000 and then minus 30,000, 50/50. Yeah. So can you calculate using certain equivalent and risk premium? And what will be your decision? Yeah, you can use this value. Okay, you can use this formula to compute the certain equivalent. Okay, so given the expected utility, okay, and the utility function that we already give here, okay, we can determine the cash value, okay, which is exactly equivalent. So this is the formula for utility, right? So then I can put this in the other side, okay? This one going there, so we have this value. Then we can calculate the X here. Okay, so given the utility, you can actually compute the payoff. Yeah, this payoff now become the certain equivalent. Is this clear or not? That's why certain equivalent is put in the slide of utility theory instead of in the risk analysis. Okay. Even though it's related to EV, but how are we going to calculate the certain equivalent? It's based on utility. Okay, so this is continuation of earlier. So if you know the utility and you know the R, you can calculate the certain equivalent. Okay, so now how are we going to decide based on certain equivalent? Yeah, so you always choose a positive CE. Yeah, the CE is this X. Okay, so you always choose positive CE, and you always select the highest CE. Yeah, there is also possibility of error. Yeah. So and then you can check also the value of RP, the risk premium. So because the negative RP is usually associated with risk-seeking behavior. Okay. Can you try this practice so that you will understand better. So earlier we already compute, okay, in practice 5 with R equal to 5. So we already computed this value, right? I think Win Sanchez was able to show that. Okay, so you can use this value, okay, the utility. So from that utility, can you calculate the certain equivalent and risk premium? Is this instruction clear, or is there anything confuse you? You can ask. Okay. I will stop sharing. So can you share this? I mean,
Okay, sir. Okay. Using the earlier output, now we're just computing CE.
right.
So using that formula, negative R ln of 1 minus expected value of the utility. So you get on both sides. This one is 60,000. Without the round of error, it should be equal to this.
Yeah, yeah.
And then the other one is negative 26. Then for the RP,
Yeah, the EV minus.
it's the difference between 60,000 and the CE of option B, 86,000.
Okay. So the RP is supposed to be 0 for
For the
option
other,
A, for option A. This
For
is for
option
option B. Yeah, yeah. This is for option B. That's good.
for option A, yes. It's
Yeah.
0.
Okay. So the RP should be 0 for option A, and then for option B, that's correct. 80,500. Yeah.
So for the decision, you select the higher CE,
Yeah.
which
CE.
is
Okay.
option B.
Correct. So in this case, you will select A. Okay. So that means today you learn two things. Yeah. One is if you want to decide based on utility only, okay, then you calculate the expected utility. Okay. Another method is to use CE. So that means from the utility, you compute the certain equivalence, okay, and then you can select the decision based on certain equivalent. Okay. Yeah, very good. Hey, how about the others? Is this clear or have some problem? If you still have problem, you can ask. Okay, yeah, okay. Or you get the same result, yeah. Right. So I guess this is clear. Right. So yeah, so we get yeah, my computation have run of error supposed to be the correct one supposed to be 60, yeah, because originally 60, right? And then the second part is yeah, is the same like Win's number, yeah, 86,000. So you select CEA. Yeah, we select A because the CEA is larger than CEB. Yeah. So this is how we decide based on certain equivalent. Okay. So what's the meaning of constant risk tolerance that we use here? So the R here is constant. Okay, so we set that. So that means this is actually an assumption. Okay, that means if we change the gamble, okay, by adding a fixed additional amount of money, okay, to the decision maker payoff in all possible outcome of the gamble, then the certain equivalent of the gamble should increase by this same amount. So that means we assume, okay, if you can see this value in the formula, then this is an indicator that gamble A and gamble B are independent. Okay. So this is very similar to probability value. Okay. So that's the meaning of this constant risk tolerance. Okay. So in summary, utility theory, okay, very simple. Okay, provide the logical explanation about what is seemingly irrational behavior, why people buying lottery. That's the start of the idea. Okay, so of course, this is not include the time. Okay, so the lottery that drawn today, okay, compared to the lottery that drawn 1 year from now, okay, is different. So in that case, we can overcome this by computing the present values. Yeah. Later during the financial analysis, we can include this the value of time. Okay. So is there any question or discussion about this utility theory? This is just the beginning of utility. So we will deal with utility again and again during game theory later on. So if you have no questions, so shall we continue with the next topic, or you want a break? It's up to you.
Continue, sir.
Continue?
Yes, sir.
Okay, let's continue. You want a break? Okay, so let's break for maybe 3 minutes. Is that enough? Okay, so let's. Yeah, okay, a 3-minute break. Okay. Okay, so 7:46 in here, so 7:50. Can we come back?
Sir, I got lost in computing R using the COSIC.
Okay, cool. You can.
Yes, sir.
You can
I have no any computation, sir.
Oh, you don't have any computation?
I tried so many times, sir, but I got lost.
Oh, which part? The initial or the second part?
Using the goal 6, sir.
Using the goal sheet. Okay, so I will open again the slide. Okay. So basically what you have is you set something like this, right? You have the how much is the win payoff and the loose payoff with certain probability. So in here we set 50%, 50%. Okay. And then how much is the payoff that you play with certainty? Okay. So then we compute that using, this is the actual formula. Okay. So we can say P, okay, probability of winning, okay, multiplied by the utility of high, yeah, the utility of high, plus, of course, this is 1 minus P, okay, and then multiplied by the probability of low, no, the utility of low. It's on the utility of high and utility of low, and that's supposed to be the same as utility of certainty, yeah, indifference. So that one should be equal to C. So then we can use the formula of this utility function because we want to get R, and this utility function is actually the formula for risk-averse. Okay, so why we use risk-averse? Because majority of people are risk-averse. Okay, so if you calculate this, so you can get this kind of formula, yeah, because this is 50% and 50%. Now, if you are not using this as 50%, 50%, then you need to use this formula here. Is it clear or not? So here, I give you example of that 50%, 50%. So you put, for example, H is 1, L is 0, okay, and C is 0.5. This is the example. Okay. So how you calculate? You calculate the left-hand side of this formula, which is this one. The exponent of minus H divided by R, okay, plus exponent of minus L divided by R. Okay. And then the right-hand side is this value. Okay. So then this one the right-hand side, and this is the left-hand side, right? So what you need to do is you set the target. The target is you minus between left-hand side and the right-hand side here. Okay, so you take the difference. Okay, of course now the difference, because they are supposed to be equal, so the difference must be 0, right? So then you set the target, and which is the difference between left-hand side and right-hand side, to be 0. Okay, then you want to change the value of R. So then you can just use Condorcet for this purpose. Okay. Now, if you have different probability, okay, and the value of H, L, and C are actually a big number, okay, so you need to put this value, okay, you need to normalize first so that the value of this is between -1 to +1. Okay, so in that case, the H now become 1, the L become 0. Okay, then how much is the C? Okay, so C in this case, okay, so if you have -500, yeah, so -500 here, and then C is 250, right? And then you have 1,000. Okay, this is your H, right? And this is L. So can you see this is negative? Yeah? So the difference is actually 750, right? minus 500 up to 250. And then from 250 to 1000 is also 750. So in that case, C is 0.5 in this case, in this example. Okay, so then once you have these three values, you do exactly the same as earlier. Okay, but now you use different probability only. Is this clearer or not?
Thank you, sir.
Is it clear or still unclear? If this is unclear, I can demonstrate, but if this is clear, so we can skip. Okay, so it's clear. Thank you. Okay, so this is just how to compute risk tolerant parameter. Okay, so it's just at least you get the idea that this parameter we don't just plug in, but we have certain numbers that we can use. Okay, look at this. Okay, so if this is clear, let's go to the next topic. Okay, this is very big topic, which is group decision making. Yeah, this is actually very useful. Okay. Close this one and go to the next topic. Yeah, which is group decision making. Okay, and we will discuss the power in decision in group decision, and then we will start simple. Okay, based on aggregation of judgment. Okay, and then based on aggregation of attribute or aggregation of alternative. Okay, or aggregation of preference ordering. And you see the topics here. Yeah, so these are all different aggregation methods. Okay, and then we will discuss about voting. You think voting is just one person, one vote, but we will expand this knowledge. Okay, that you can go into different type of votings. Okay, and the last one is very interesting. We call this n-person cooperative game. So this is actually game theory already. Yeah, but instead of game under conflicts, now we talk about game under cooperative. Yeah. Okay, so let's start. Yeah. So in the big picture, okay, we are still in decision analysis. So we already discussed decision under uncertainty, yeah, or certainty, under risk and utility. Yeah. Now we are in a group decision making. Yeah. So sometimes we call this cooperative game. Yeah. In contrast, we also have a game theory, which is basically talk about decision under conflict. Okay, so actually the two of them are game theory. Yeah. So first, look, let's talk about the power in group decision. You have a team, right? And in your office or your work, in the school or in the work or organization, yeah, even in the church, okay, you also have a group decision. Okay, and if you are in academic, you also have that kind of things. Yeah? So group decision is usually binding for all the members in the group, isn't it? Okay, so and usually we do vote. Yeah? Those who lost in the vote must comply, even if you don't like the decision. Yeah? The same in the country, you have group decision to select, yeah, your government officer or your president. Okay, so whether you like it or not, okay, if the majority or the based on the rule of the voting win, then you must comply. Okay, now question is, what if those who lost does not want to comply? Okay, then the next question is, does the group or the leader have the power to force them to comply? Okay, democracy is, we talk about voting, right? Democracy is not just about voting, it's actually about power also, yeah? So can we force them to comply? Yeah, if there is no way to force them to comply, then the vote is actually meaningless, yeah? So I give you simple example. This is based on last time I have a project, okay, in the Philippines. So, and then the leader of the project asking to vote, okay. Shall we finish the second year project at that time, okay, in February, or we finish the second year project in March? So between February and March, we need to vote, okay, because we want to start the third year project, okay. And if we finish in March, okay, we are not sure when we will start the third year project, because there was an election, upcoming election at that time, okay. And the group have 10 people, so we vote, yeah. So 7 people vote February, 3 person vote in March. So who win? February, okay. So supposed to comply, these 3 supposed to comply, right? But the project leader has no power to force them to finish earlier. So then eventually the project cannot continue, yeah? Because not all members finish. So in this example, who win the vote? Okay, 3 or 7? Okay. During the vote, yes, look like 7 vote win. Okay, but based on this reality, okay, who has actual more power? The one that say vote in 3 vote in March actually have more power. Yeah, so we can say those who cannot finish in February, which is in March, they have veto power. Yeah, what is the meaning? They have a higher vote value compared to those who can finish in February, isn't it? So what is the point here? Okay, the point is vote is not always 1-to-1. Okay, there are certain weight that you can assign to the vote, okay, that eventually can veto the power of the whole group. Okay, so the idea of group decision is based on what is called aggregation function. That's why we will discuss a different type of aggregation function. Okay, so voting is one of them. Okay, so group decision or group choice is basically an aggregation, okay, summarize the individual preference, isn't it? Okay. Group consists of individuals. So now depending on what is the aggregation function that you will use, okay, so this aggregation function, okay, we often call this as social welfare function, yeah? So that's just the jargon, okay. Next jargon that I want to discuss is about unanimous and consensus. So what's the difference? Okay, so when we say consensus, okay, that means it is an agreement made by the group, okay, to ultimately lead to collective decision. Okay, so the concept of consensus sometimes defined as 100% agreement, but this is not correct. Okay, 100% agreement, that means unanimous. Okay, can you see the difference? Okay, consensus is not the same as unanimity. Okay, unanimity or unanimous means 100% must be agreed. So yeah, when I was students, there was a conference, a national conference in Indonesia, and they tried to create unanimity, okay, and they start lobbying each other and just to make an agreement. But for 3 days and 3 nights, we start to discuss the same thing, and we cannot make an agreement. Okay, and eventually the Congress failed to create an agreement. So why? Because they don't like consensus. They want unanimity. In contrast, if you understand consensus is better than unanimous, okay, then when there is a consensus, everyone just agree on something. For example, you want to go to a movie with friends, okay, to reach consensus, okay, everyone want to see that movie, but doesn't mean that everyone must agree, right? So consensus, okay, usually computed as majority. Okay, what is the meaning of majority? Okay, majority is basically just 50% plus 1. Yeah. So we said strong consensus occur when the opinion is widely shared throughout the entire population. So remember, no need to reach unanimous or unanimity. Is that clear? So in the group decision, we don't need make 100% people agree. Yeah, it's just majority is fine to reach what is called consensus. Okay, so for that, we start to see now what is the aggregation function of the social welfare function. Okay, given any set of individual preference, say we have 3 persons here, Ali, Buddy, and Cherry, so A, B, C. Okay, so given any set of individual preference, so the aggregation function will determine the particular aggregate is aggregate in the summary of the social ranking. Okay, so Ali prefer X over Y over Z. So these are the rank of Ali. Okay, Buddy prefer Y over Z, and then the lowest is X. Cherry is the other way around. Cherry prefers Z over X, and then the lowest is Y. So these are the problem. Okay, so which one we should select? Yeah. So there is a problem of inconsistency in this example. Okay, which actually observed a long time ago by the Marquis the Condorcet. So that's why this is called paradox. Yeah? Condorcet paradox. Okay. Later we will discuss more detail about this. Yeah? So let's start with the simplest aggregation function. Okay, or social welfare function, which is a simple aggregation. Okay, so in simple aggregation, the judge, you, everyone have equal weight, and then you have equal voting weight. That means you assume individual are unbiased toward estimating or there is no overestimate or underestimate. Okay, so when we say estimation, okay, we have the true value and there are certain error. Okay, the idea of simple aggregation means you have reliability of estimation, okay, will increase if the number of the group size increase. Is this true assumption or not? Okay. They thought that if the number of group size increase, okay, then the true value become average out, and the random error become average out, so the true value will reveal by itself. Okay, so this is the idea or the assumption behind simple aggregation. Okay, some say true. Okay, but there's some problem with simple aggregation. What is the problem? The problem is crowd behavior. Okay, people tend to follow the flock. Yeah, similar to this duckling following the mother duck. Okay, so if the first person overestimate, then the others will get influenced. Okay, so in fact, reliability does not increase much after 5 individuals. Okay, I give you example so that you can start to see how we compute the reliability. Yeah, reliability is the inverse of standard deviation. Okay, so say you have 3 judges, yeah, A, B, and C. You want to estimate certain project. Okay, so A said 3 million, B said 1 million, and C said 5 million. And then the estimation become 1 plus 3 plus 5 divided by 3 judges. So the estimation become 3 million. Okay, so this one is called simple aggregation. Yeah, simple aggregation. You have equal voting weight. Okay, so let's contrast this with the second aggregation function, which is, of course, weighted average. Okay, so what we do, we normalize the weight on the expertise of the judge. Okay, so now we don't assume equal. Okay, each judge will have, certain judge is more expert than the other. Okay, so because they are more expert, they will get higher weight. This is an example in election in Japan. Okay, so instead of 1 man, 1 vote, they use a portion electoral system. Okay, which will give more weight to underpopulated rural district. Meaning farmer will get 5. If you are family of the farmer, you will get 5 votes. Okay, so that's why certain party, yeah, LDP, always win. Yeah, in Japan, I think they lose only once or twice in the whole history of Japan. Yeah, so they use weighted average. Okay, so back to this example earlier, if we use weighted average, what we will have? Okay, so we will say judge A. Okay, now we put the weight to the judge. Okay, judge A is 2 times more expert than judge B. Okay, and judge C is 3 times more expert than judge A. So then we will say A is 2 times than B, C is 3 times than A. So in that case, we can compute. Yeah. So if we put B is equal to 1, then A is equal to 2, right? So in that case, A is 2, then C become 9. C becomes 6, yeah. 2 times 3, yeah. So this is now become the weight. Okay. How to compute is here, 1 divided by the sum. So the sum is 9. 1 plus 2 plus 6 become 9. So 1 over 9, and then 2 over 9, and 6 over 9. So these are the weight for the judge. Okay. So once you know the weight, then put back to the estimation earlier. Okay, then now we have the estimate now instead of 3 million now become 4.11. Up to here, is this clear or not? The second aggregation function is based on weight. Okay? Clear, yeah? So now there is a town in Greece long time ago called Delphi. Okay, so they create a technique. Yeah, this is very well known method. Okay, so we call this Delphi method because people in Delphi at that time they use this method. Okay, this is an iterative group decision process. Okay, where the panel of expert you will give the estimate on the weight or the value based on your area of expertise. Okay, so we will play in a moment about this. Okay, and each person will have opportunity to reevaluate your own response after a feedback based on the aggregation value. Okay, so the judge does not know the estimation of other judges, so that they will not follow the bias value. Okay, and let us see, okay, that this is the good things about Delphi method. Yeah, the result usually converts after several rounds of feedback. Okay, shall we try this in the class? Okay, so let's say I have this phone. Okay, so let's practice. Okay, let's practice Delphi method. I have this phone, okay, or possible cost of development project. So let's say the phone, can you estimate the price of this phone? Okay, so instead of development project that you don't know, so let's talk about this phone. Can you estimate the possible price of this phone? Each of you. Okay, so each of you will give your own opinion, okay, because we are online, so we don't use paper. So can you chat me personally? And then I will put your opinion, okay, in Excel. Okay, and then I will compute the average and then the standard deviation. Okay, and then I will give you the feedback. Okay, which is the average and standard deviation. After that, you evaluate again. Okay, 3 times. Is that okay? Let's play this game. Okay, make it the same currency. You want in USD or in pesos? Okay, let's make it in pesos. I will open Excel. Okay. So let's start. I will not give you the name, so I'll just put the one in the chart. 50K. Okay, 50K. Yeah. Yeah. 30K. Okay. 20. How much? 35. 25. Any other number? 50 again. Okay. 45 and 50. Anyone want to give opinion? Okay, last opinion. Okay. 45. Okay. Okay, so let's take the average, okay, and standard deviation. Yeah, STD. Okay. So let's take the average and standard deviation. So I will say average of this. Okay. And then I will say the standard deviation of this. Yeah, that's def. Okay, let's put in population so that easier. Okay, so I will just give you back feedback. On average, okay, on average is 37.5. Okay. Let's start with round 2. Okay, so this is round 1. Okay. Can we do round 2 now? Okay. I give you feedback. Those who said 50 earlier, okay, what is your number? Okay, the average is 37.5. Okay, let's start. So 32. Okay, 26. 35. What else? Okay, those who give opinion earlier, so please put. Okay, so 35, 32, 39, and then 40, and then 30, and last one is 42. Okay. Okay, so let's copy this. Oh, okay. Hey, based on the second round, okay, we have 34.5. Yes, can you see the standard deviation reduce? More reliable. Okay. You want to go to the third round? Okay. So give your opinion. Opinion only. Okay. So you said now become the one in 32 now become 25, 35, and 31.5, and 39, okay, and 32.5, and 33, and two more. Who gave 30 earlier? 31, and last, any number. Okay, 29. So let's see. Okay, so we copy this, and wow. Okay, can you see the standard deviation here? Okay, so you're telling this is 32,000. Okay, and the most important is actually the reliability, isn't it? Okay, so the reliability is now getting smaller from 10, now become second round become 5, third round become 3. Okay, so when I give you the feedback of this, yeah, so then you can start to see Delphi method will actually make your decision converge. Okay, and this is nice. Yeah, nice way to do a group decision, isn't it? Okay, so is it clear? Delphi method, you can do it in your office, in your group, also in your project. Okay, very simple method. Okay, give back the feedback about the average and standard deviation. and then do several rounds. Okay. Usually it will converge. Yeah. Three iteration is, I think, enough. Okay. So this is the next function. Yeah, we call this aggregation by attribute. Okay. Now, instead of aggregating by the final estimation, okay, now each individual you will estimate the probability of each criterion. Okay. And then you will take a simple average of individual probability. Okay. So I give you an example here. So say you have two judges, X and Y. Okay. And there are two factors, yeah, A and B. Okay. So what happened is judge X say factor A is 0.2, factor B is 0.6. Yeah. Judge Y will say factor A is 0.4 and then factor B is more important, it is 0.9. Okay. Both are actually consistent, yeah. Factor A is less than factor B, right? So then you multiply. So you get 12. And then if you multiply these two, you will get 0.36. And then you get the average. Okay. Now compare this. What will happen if you take the average first? Yeah. So 0.2 and 0.4, the average is 0.3, right? 0.6 and 0.9, and then the average is 0.75. And then you multiply. Okay, you will have different values. Okay, so if you multiply each just probability, then take the average, okay, you will get 24%. But if you first aggregate individual probability, and then you multiply, you will get 22% and 22.5%. So, okay, so you aggregation by attribute, okay, instead of aggregating the final estimation, okay, now each individual will estimate the probability, and then you take the simple average of individual probability. So, meaning you're supposed to get 24, yeah? You are not supposed to get this. Is this clear or not? Yeah. So be careful. Don't take the average first and then multiply. Yeah. You take for each and then you average that. That's the way to do aggregation by attribute. Okay. Why? That's the question. The problem is actually rank reversal. Yeah. So let's talk about that in this next aggregation function. Okay. Instead of doing factor or probability, now what will happen if we aggregate by the rank of the alternative? Suppose you have three judges, yeah, X, Y, and Z, and then you want to decide, okay, three projects, yeah, A, B, or C. Okay, so question is which project you should select. Okay, so judge A prefers C, then A, then B. Judge Y prefer B, then C, then A. Yeah? Judge Z prefer A, then B, then C. Okay, so how are we going to select? Okay, so what happened is we take the pair, right? So we take the pair. So A larger than B. How many times? This one, A larger than B. This one, A larger than B. So 2 times. So A larger than B get 2 votes. Okay. So how about B larger than C? This one, B larger than C. This one also B larger than C. So B larger than C get twofold, yeah, C get only one fold, right? So if you compare this, you will say, okay, in that case, A larger than B get twofold, and B larger than C get twofold. So you will conclude this way, right? But let's compare the other way. How about the C larger than A? You also get twofold, right? So in this case, your group decision, even if individual decision is transitive, okay, your group decision is contradictory, right? Okay, so this is a problem in group decision. Okay, so this is called Condorcet paradox earlier. Okay, now not only that, okay, in group decision, okay, sometimes we don't see things immediately, isn't it? So there's a sequence of the alternative. So the sequence of the alternative matters. Okay. If the alternative is not compared simultaneously, but consequentially, so then the order of comparison also have direct effect. Okay. So say if the group will compare A to B first, okay, and then you eliminate the inferior alternative, okay, and then compare the superior alternative to the next alternative, A will win. Okay. If A compared to C, okay, C will be chosen. But if the group compare B to C first, okay, B will win. And then compare to A, and then A will be chosen. So this is a problematic, right? Okay. So say if the group compare to between A to C first, then C will win, right? And then if you compare C to B, then B will be chosen. So in the summary, there is a cyclic here, okay? Depending on which you select to compare first, okay? If you begin with A compared to B, like this, A compared to B, yeah, then the choice is C. If you begin with B compared to C, the choice is A. The same thing, if you begin with comparing A to and C, and then the choice is the one that not compare first. Can you see that in this paradox? Okay, so what is that means? Meaning group choice by majority rule is actually arbitrary. This is shocking, right? You always choose by majority rule as consensus. All right. But actually, when you choose by majority rule as consensus, that rule is actually arbitrary. Okay, that is actually irrational choice. Okay, so we put here, such choice is actually irrational because it can lead to inconsistency in decision process. Okay, and this is one of the example which is called Arrow paradox. Yeah, Kenneth Arrow, okay, notice this, and based on this, you can actually cheat based on the information and the sequence. Yeah, in decision theory, you can actually cheat, okay, in a group decision. So how to cheat? Okay, here. So in the sequential alternative, okay, a clever group member would actually cheat by being dishonest. Okay, so I put quote cheat in here. Why? Because this is being dishonest about his own preference. Okay, so you simply not revealing your own preference first. then you may win. Wow. Right? So the last person who say in the group, okay, will win. Okay. Simply by being dishonest to your own preference. Okay. Simply by delaying your decision and listen first. Okay. The clever group will eventually win. Okay. Okay. Let's see how this go into the example. Okay. Say this is the clever group that will cheat, yeah, Z. Okay, this is actually his or her decision, his preference. Z will actually supposed to choose A larger than B larger than C. Yeah, in this example. Okay, now, but Z delay the refilling. Okay, his or her preference. Okay, so suppose X and Y show this value, okay, this preference. Now, suppose A compared to B first. Can you see this? A compared to B first, okay? So Z knows using this value, if you put A compared to B first, okay, then letter C will be with this list in this preference will be chosen. He doesn't like that, right? Okay. So then he lied to his own preference. He said, no, I don't want this. Yeah. Actually, what I want is this one. Yeah? B larger than A larger than C. With this one, okay, we'll make B win, yeah, not A in the first round. So then B will defeat C in the second round. Okay, so in the first round, B is larger than A with two-fold, right? Yeah, B is larger than A two-fold. And then in the second round, B is larger than C with two-fold also. So by lying about his own preference, does not reveal it and then change his mind, what he's saying, okay, he can control the group decision. Can you see that? Any question about this? Yeah. So this is actually a wow, right? So we can actually do this. So, and in fact, yeah, this is what is called Arrow Impossibility Theorem. Yeah. So, Ken Arrow said that he asked whether there is there any satisfactory method to determine group preference when the preference of individual members are expressed in order? Yeah. So, and he mentioned about 4 conditions, okay, that satisfactory procedure should meet. Okay, this is the assumption. Yeah. So he only assumed order of preference, yeah, not include intensity of preference. So it's just transitivity. Yeah, the order is important, not the numbers, how much. Okay, so what are the 4 conditions of Arrow? Arrow is the name of person. He won a Nobel Prize, yeah, in economics for this exact theorem. Yeah, that's why we call it Arrow Impossibility Theorem. You can search in Google. Yeah. So what are the 4 conditions of Arrow? Yeah. So number 1, the method should produce transitive group preference order. So this is unrestricted scope. Yeah. So meaning rational, right? So transitive means rational. Okay. The second condition of Arrow said, if every member prefer one option to another, so the group must also do the same. So this is based on Pareto principle. Yeah, when every individual prefer X to Y, then of course the aggregation function, okay, should be the same. Yeah, so the group must reflect the individual, right? So the third one, the third condition is group choice between two alternatives, yeah, A and B, depends only on the preference of members between this alternative. Yeah, is not on the preference of any other option. So that means individual cannot cheat. Okay, so earlier that we give example of cheating is not allowed. Okay, so this is called independent of irrelevant alternative. Yeah, IIA. Yeah, so you focus on certain alternative. Okay, don't care about the other alternative. Okay, the last one is no dictatorship. Yeah, no individual can impose his or her preference to the group. Yeah. This is also important condition. Okay, so the aggregation function, okay, must based on this four condition. Yeah, so we call this with a name. Yeah, so U, P, D, and I. U is unrestricted scope. Yeah, P mean Pareto principle. D mean non-dictatorship. Yeah. I mean independent. IIA, independent of the relevant alternative. So what Kenneth Arrow did, yeah, that he can won a Nobel Prize, he proved that no aggregation procedure can guarantee to satisfy all those four conditions above. Yeah, that means only three conditions can be satisfied, but not four. That's why they call it impossibility theorem. Yeah. So this is significant yet actually depressing result. Yeah. So it is impossible to derive a truly democratic system to resolve difference of opinion. Yeah. These are the implications of Arrow Impossibility Theorem. Okay. So is there any question here about these things? Yeah. So if not, so let's discuss about the next topic, which is voting. Yeah. So voting and coalition. We talk about politics, but at the same time, I think this is also very important when you are in transportation groups or in urban planning. Okay, this is also part of the tool that you can use. Yeah. So a vote is a formal expression of opinion or a will. Yeah, in response to a proposed decision. Okay. So when we say voting, mean you cast or conduct a vote. Okay. So election is a formal or organized choice, okay, by voting of a person or a political office, yeah, or other position. Okay. So when we say coalition, that means alliance of combined action. That means you have a kind of cooperation. Okay. So remember this, yeah. Coalition is always temporary alliance, okay, of the political parties forming a government or a state. Okay. So let's discuss several types of voting. Okay. So then at least this, even if you don't use all of them, at least knowing all of this will expand, okay, your open mind. Okay, will open a new direction in your thinking. Okay, so there are many types of voting. Okay, so let's keep name for this a few types. Yeah? So we have priority voting, we have cumulative votings, runoff votings, negative votings, and approval voting. Okay, so what is priority voting? Okay, let's start with the first one, priority voting. In priority voting, okay, each voter casts one vote or no vote for the given candidate. Okay, remember the candidate here is not necessarily a person, yeah, can be a project, okay, can be a state or condition. Okay, this is basically an alternative that you want to decide in a group. Okay, so the candidate with the largest vote total are declared to be elected. See, this is an example. So you have 8,000 voters to choose 5 candidates, right? So how much? 8,000 divided by 5 is how much? So let's take a half of that. So 8,000 divided by 2 is 4,000, right? So if we say
1,000.
yes, yeah. So if we take divide by half, yeah. Okay, so if you have a coalition, if you can create a coalition of 4,001 member, that means half of this plus 1. Okay, then you can select any candidate by your own choice. Based on plurality rule. So why? Because any other candidate will receive only less than that majority, isn't it? Yeah. So remember, yeah, in plurality voting, okay, each voter will cast only one vote or no vote for the given candidate. Okay. Next is called cumulative voting. So in cumulative votings, each voter may cast a total of E vote. Yeah, E is the number to be elected. Okay, and then they can distribute this E among as many candidates as desired. Yeah, E is not necessarily integer. And then the candidate with the most vote are declared elected. Give you an example. Okay, say you have 4 voters, say A, B, C, D. Okay, and you have 3 candidates, X, Y, and Z. Okay, now suppose E in here is 5. So each voter will have maximum can cast 5 votes. Okay, to elect this 3 candidates. Say suppose B can give 3 votes to X, 1.5 to Y, and then 0.5 to Z. Yeah, the total is still 5 votes, right? And then D give 4 votes to Z. Okay, so no need to maximize up to 5. Okay, and then you just sum for X, for Y, and for Z. Okay, so in this case, you will get who will win. Is this clear or not? Okay, you make an agreement about the maximum of votes, and then each voter can select, can give the vote to the candidate, yeah, whatever they like, as long as the total is 5. Yeah, the total is E. And this is called cumulative voting, and very rare to be used, yeah, because you have different numbers here. Okay, but this is also interesting. Yeah. So suppose V is the number of voter, N is the total number of vote cast. Okay, and then small n here is the total number of voter in a coalition C. Okay, and E is the total number of candidate to be elected. Okay, so we assume the total number of voter should be larger than the total number of candidate. Yeah, this is the main assumption here. So this is the theorem. Under that cumulative voting, okay, a coalition C with n voter can guarantee to the election of Y candidate. Okay, the Y is computed by this formula. Yeah, this symbol means floor function. Yeah, so you multiply n by E divided by V. Yeah, hey, I'm talking about voting, but we can also get the mathematics of the voting, isn't it? Okay, so I give you an example so that you can understand this. Okay, suppose you have a coalition of 46 voter. Okay, so the total number of voter V is 81. Okay, and the number of candidate to be elected is 8. Okay, so then the question is how many candidate the coalition can elect. Yeah, so we use the same formula a while ago. So the coalition of 46 vote, yeah, can elect at least 4 candidates among the 8. Can you see this? How do you get that? You know, n is 46, yeah, multiplied by the number of voter, which is 80. E is 8 here, and then divided by the total number of voter, 81. So then this one, you can take the floor. Yeah, floor is the largest integer below this value. Yeah, in this case, 4. Yeah, so this coalition, when it gives by giving each of the 4 candidates 92 votes. Yeah, these numbers. Yeah, 46 times 8 divided by this 4. Okay, you will get actually 92 votes. Yeah, so actually the coalition can elect 5 candidates by giving each of them 73.6 votes. Yeah, so if you use cumulative voting, yeah, so this is things become more interesting, yeah, because now you can start to create coalition in order to win the election. Okay, how many people can you select? Yeah, these are the mathematics of voting in cumulative voting. Okay, so this is quite interesting. So the next one is called runoff voting. Yeah. I don't know. Certain country have this kind of system. Yeah. So you vote for one candidate as in the plurality voting, the first one, plurality voting. Yeah. One vote or no vote. Okay. And then if there is a tie, okay, so the runoff for the second round is permitted between the top, yeah, 2 vote getter. Yeah, if you cannot find the majority vote in the first round. Plurality voting is presidential voting system in the Philippines. Okay. Brazil have runoff voting. Indonesia also have runoff voting. Yeah. Good. Okay, so this is some countries are using this technique. Yeah. But this is very expensive, yeah, to do the second election. Okay. So the next one is called negative voting. Yeah. So in this case, each voter can cast either a vote for a candidate, so +1, or vote against. So this is not 1 and 0 or binary, but 1 and -1, but not both. Now, this is more interesting. Yeah. So instead of 0 and 1, you can have 1 and -1. Either vote for or against. Yeah. So the voter cannot vote for and against more than one candidate. Okay. Then the candidate with the highest net vote wins. So with this, you can avoid expensive run of votings. Yeah. So there is no run of voting even if no candidate is actually positive. Okay, so this is interesting. Another way to do voting. Yeah. So not always plurality voting. That's the message here. Okay. So the next one is called approval voting. Approval rating. Yeah. So this is simple, robust, and practical. So you vote for one or more candidate. Yeah. It's not just one vote one. Okay. A voter can cast a single positive vote for as many candidates as she wishes. So voter is more powerful here. So the voter can vote between 1 up to the total number of candidates. The good thing is no runoff election. Not necessarily. Can be for negative voting, can be for politics as well. Yeah. Yeah. So the politics is based on agreement. If you can make share idea about this, once you learn this, okay, make this into share idea, and you think this is good, then share this to many people. Then this can be become politics. Okay, so politics is based on shared ideas. So approval rating is actually simple, robust, and actually very practical. Okay. The individual will vote for all the alternatives that they think at least acceptable. Okay, so instead of voting for one, they can choose as many as they want. Okay, so also in group decision. So if you want to find alternative that you want to receive the most vote, then you can use this also in the team. Okay, so there's a problem. Yeah, correct. So this is kind of survey. Okay, who will select? Yeah, which option prefer? That's correct. So the problem is we ignore the information about individual preference. Yeah. So this is also non-Pareto. Okay. Is there any question or discussion about all of this type of voting? Yeah. So anything? No? If not, let's discuss the last part of the topics today, okay, which is n-person cooperative games. Yeah. So in many voting situations, okay, it can be represented as weighted majority games, okay, meaning that more than half, right? So this is, say, suppose there is a quota Q and the weight I. Now, WI exists in each player, okay, then you're supposed to form a coalition to win, okay? So, meaning if your sum is larger than certain quota, then that coalition will win. So this is called n-person cooperative games. Yeah? This game, you have n players, so each player is represented by the weight. yeah, W1 to Wn, and then there is a quota Q here in the beginning with semicolons. Okay, so you assume that Q must be larger than half of the weight, all the weight. Okay, so this is what we will do. Okay, so that you can start to see. What is the application? Yeah, so you can apply this to politics, to business, and so on, even to projects. Okay, so the percentage of the company stocks that an investor own can serve up the weight, right? So individual or the coalition over 50% of the stocks have full control, okay, about whatever decisions are made by simple majority vote. Okay, so a group or coalition with more 50% or more of the share of the stock can veto or block such action. Okay, with that we can start to see how we can simplify, okay, the voting into power. Okay, so let's see here. Suppose you have each person have 1, 1, 1, 1, 1, and then you have Q. Yeah, remember this Q is more than half. Yeah, this Q must be more than half of the sum of the weight. Okay, so in this case we call this each player have equal power. Yeah, if everyone have equal vote and the Q is just more than half of the sum of the weight, right? And next, player 1 here, this is the Q is the quota, and the quota is 51. Okay, player 1, 28, is actually stronger. So this is player 1 have stronger power than the last 3 other players. See, in this example, we have 4, right? We have 4 players. Okay, the first one is 28. The weight is 28. The second one is 24. The third one and the fourth one is 24. Okay, so why we say player 1 is stronger? Okay, because a player 1, in order to win, okay, she need only one other player. Can you see this? 28 plus 24, how much? Yeah, so 28 plus 24 is larger than the quota. Yes. Yeah. 50, so 52. Okay. Yeah, 52 is larger than the quota. Right? So meaning player 1 need only one other player in order to create a coalition to win. Clear, yeah? That's why we call it stronger player. How about this one? Okay, the last player, player 4, is called powerless. Yeah. Why? because any winning coalition containing her is just as well win without her. So, okay, so now you can start to compute, yeah, the mathematics of voting. Yeah, so you know the quota and you know the power. So you can see who actually have the power and who doesn't have the power. Yeah, simply by computing. Yeah, so if they make coalition, say these two or these two, okay, or these two, okay. So without including the last player, they always win anyway. So the last player is powerless. Okay, in the UN, we have what is called veto power. How are we going to put that into mathematics? Yeah. So a player or a coalition said to have veto power if no coalition is able to win a ballot without his or her or their consent. Okay. So in here, this is an example. This is the quota 51. Okay, we have only 3 players. So these are the value 50, 41, 49, and 1. Can you see this? Okay. This is called veto power. Why? Because player 1, okay, can veto whatever the others. For example, player 2 and player 3 make a coalition that is the same, 50, which is below 51. So, okay, unless they said yes, it will not happen. Okay, the same thing here, as simple as 3, 1, 1, 2. Yeah, so 3 here is the quota. Okay, so player 3 here has veto power. Okay, because if they make coalition, okay, without her, cannot make decision. Can you see that? So how about in the UN of the 5 permanent members, okay, in the Security Council? Okay, in the UN Security Council, you have 5 permanent members with veto, and then 10 non-permanent members. Okay, so if you put that, then this is the actual numbers. So this one is the 10 other non-permanent members. They have all one veto, one vote. Okay, the 5 permanent member have 7 vote. Yeah, and you need to get 39. Yeah, in order to make decision. So this one alone, okay, 5 times 7 is 35, right? So they need only 4 non-permanent member in order to create the decision. But without any of this, yeah, for example, one of them did not want. Okay, so what is the value? Okay, that is 10 plus 28, still 38. So cannot make decision. Clear, yeah? So, and then when you say dictator, okay, how are we going to put numbers into dictatorship? Yeah, a dictator is a voter J is a dictator if he control any vote by himself, that is his weight is larger than the quota. Okay, so there can only be one dictator and other players are called dummy. Okay, the player who has no real voting power is called dummy. Can you see this example? Okay, so the quota is 3 and this is exactly 3, right? So that means player 2 is a dictator. Why? Because player 1 and player 3, whatever they vote cannot make decision. Okay, can make coalition, yes, but player 2 alone can make decision already. Can you see that? So dictator does not need to win all, okay? Just simply make the weight equal to the quota. As simple as that. Yeah, so it's not always the dictator mean take all. Okay, so this is the simple values, okay, which represents similar in terms of power. Okay, so this one, yeah. Even though the numbers are different, okay, but in terms of power, they are similar. Why? Because they will give rise of the same collection of the winning coalition. Okay, so in order to win 3, okay, the 2 of them, okay, number 1 and 2, yeah, player 1 and 2 must make a coalition. Okay, so coalition of at least 2 is needed in order to win the decision. Okay, so then the following game is called identical in terms of voting influence because the same coalition are winning in both cases. Okay, they are the different numbers. Okay, but if you want to win a 51, okay, you need to join the same coalition. Okay, so this is 51. If you join 40 and 10 is less than 51, so you cannot win that. Okay, so you need to get 40 and 20. You can to win this decision 51 and so on. So the same number of the same coalition, okay, the same players. So it means they are identical. So with this, I hope it is interesting enough for you. Okay, that we can make group decision, and there are some mathematics, yeah, in the group decision that you can play. Okay, so thank you everyone. Okay, and happy Easter.
Thank you, sir. Happy Easter.
Thank you, sir.
Yes, bye bye.
Thank you,
Happy
sir.
Easter.
Yeah.
Bye-bye.
Bye bye.